Welcome to lecture 24 of electromagnetic field and waves. So let's just quickly review what we did last time. So we started our treatment of transmission lines. And we said that transmission lines can basically be denoted by the following symbol. You essentially have two parallel conductors. And in general, this is your transmission line. And you will see in a few lectures that in general you apply some. So this transmission line basically transports electrical energy and signals from some source S to some load L, and this part is the transmission line. We did a time domain analysis. Of a lossless transmission line, and so graphically speaking, what we did was we divided our transmission line into many small segments of length delta z, and so our lossless transmission line looked something like this, where we basically had the first conductor. This was connected to an inductor. There was a shunt capacitance. This was the second terminal. And then you had another inductor, and you had another capacitor, and then another inductor, and another capacitor, so on and so forth. And basically, for example, this length was delta z, and so in one delta z, you basically capture an inductance of L delta z, you capture capacitance of C delta z, L delta z, C delta z, L delta z, C delta z, and you basically apply a voltage signal V of zt along these terminals, and that signal then propagates to the right or to the left, whichever way the signal is propagating. So this was the transmission line model. What we did was we labeled these terminals. We called this node 1, we called this node 2, we called this node 3, and we called the voltage at node 1 V, we called the voltage at node 2 V plus delta V, and we called the voltage at node 3 V plus 2 delta V, and then we called the current leaving node 1 as I, we called the current leaving node 2 as I plus delta I, and we called the current leaving node 3 as I plus 2 delta I. What we did then was that we applied Kirchhoff's current and voltage laws, and we came up with the Telegraphers Equations for lossless transmission lines. And the Telegraphers equations for lossless transmission lines, they basically were that partial V of Zt by partial Z is equal to minus L partial I of Zt by partial T. And the second Telegraphers equation that for a lossless transmission line was that partial I by partial Z was equal to C partial V by partial T. And using these, we wrote down the wave equations for a lossless transmission line, and the wave equations that we had written were that, well, the first wave equation was that del 2v by del z squared is equal to LC del 2v by del t squared. This was the first wave equation, and the second wave equation that we had was that del 2I by del t squared is equal to LC del 2I by del t squared. We saw that the speed of propagation v, the phase velocity, was equal to 1 over the square root of the inductance times the capacitance, which is basically which was this factor here. And we saw forward and back propagating solutions. And the last thing that we derived last time was that we came up and derived something called the impedance, which was the ratio of the voltage at every point to the current at every point. And that impedance, we called it Z0, which was in fact called the characteristic impedance. So, and this characteristic impedance we saw was equal to the square root of L over C for a right traveling wave. So this was basically a time domain analysis, and this was basically this was revision. Now today what I want to do is two things. So today's agenda is twofold. The first thing is that I want to introduce to you frequency domain analysis. In other words, we'll call it phasors. And the second thing that I want to do is that I want to start our treatment of a lossy transmission line. So far, the transmission lines that we have assumed, so I mean, you get this characteristic impedance. So this is lossless, and that's because we assume that there's no series or shunt resistance. So there's no resistance for electrons moving across the conductor, and there's no leakage of electrons from one conductor to the other. We completely ignored this, and in this lecture we will pay heed to this. But so we'll do lossy transmission lines in this lecture. But the first thing that I want to do is that I want to introduce, well, for the double images, this might be revision. For the non-double images, this is just a fancy word for complex analysis. But I think it's good for the physicists among us also to know this. So I want to introduce phasor notation. So phasor notation is basically it makes solving differential equations and handling impedance simple. So the idea is the following. So consider a sinusoidal time varying voltage wave. It's a traveling wave. Okay, so for example, so V of zt is equal to some V naught cosine of kz plus or minus omega t plus phi, right? So that's a typical sinusoidal traveling electromagnetic wave. Now we know that we can write this exactly like the real part of a complex exponential, where the complex exponential is just V naught e to the I of kz plus or minus omega t plus phi, right? Nothing new here. And the real voltage is just the real part of the complex exponential voltage. And we know that exponentials are easy to work with, and the reason for that is that their calculus is very simple. Now, if I were to write, I know that the physical voltage is a real part of the complex voltage, but if I would just want to write the complex part separately, so the complex voltage is just V of zt, which is V naught e to the I times kz plus or minus omega t plus phi, which we can write as V naught e to the power I phi. Phi is just some initial phase times e to the I kz, where k is the propagating vector, z is just dimension. It's the axis of propagation, times e to the plus or minus iota omega t, right? I is a complex number. Now, if I were to define if I was to define this factor, because you see, if I were to define this factor as V naught tilde, right? So this is the complex amplitude of the voltage. Then I can write my full complex voltage, which is V of zt. I can write it as V naught tilde e to the I kz e to the plus or minus iota omega t, right? Where V naught tilde, where V naught tilde is the magnitude of V naught e to the power I phi, right? So this expression here, so this expression here this is just the complex instantaneous voltage, right? This is just the complex instantaneous voltage, and the real physical voltage would just be the real part of this. So the real physical voltage would just be the real part of the complex instantaneous voltage. Now here's the fun part, if we can call it that. So we define the phasor voltage as follows. We define the phasor voltage, I'll call it V subscript P because it's just phasor, as V naught tilde. V naught already has the factor of e to the I phi. So we define the phasor voltage as V naught tilde e to the I kz, right? And we basically, so when we talk about the phasor voltage, when we talk about phasors, we ignore time dependence. And instead we assume that we assume single frequency omega, and in our whole transmission line or in our whole geometry we assume it's the same frequency everywhere, and so we just we don't specifically look at the time dependence at every point. And in some sense what we do is that we take the Fourier transform of our equations and we just look at everything in frequency domain. So we solve our equations in frequency domain. Okay, this will become clear in a second. So that's a phasor. Vp V naught e to the I kz, that's a phasor. Now I just want to make a point about a note about waves. Consider the sinusoidal voltage. Once again, V of zt is some V naught cosine of omega t plus or minus kz plus phi. Now notice that this is just like the equations we used to have. We used to have cosine of kz plus minus omega t, but rather than having plus minus in the omega t term, we now have plus minus in the kz term, right? So see, this can also represent a forward or backwards traveling wave. And the idea is that if you have, let's say, omega t minus kz, then this is right moving in z. And similarly, if you have kz minus omega t, and this is also right moving in z. So then this sinusoidal voltage, so in complex form, um, this voltage can be written as, so V of zt becomes equal to the real part of V naught e to the I times omega t plus or minus kz plus phi, right? And so that's the real voltage. So so the complex voltage becomes V of zt becomes equal to V naught tilde. The V naught tilde is mod V naught e to the I phi times e to the I omega t, not plus minus omega t. Instead, now we have e to the I plus minus kz. So now once again, if we write this voltage in phasor form, so this voltage in phasor form, this basically becomes Vp becomes equal to V naught tilde e to the I plus or minus kz. So if you have e to the minus I kz, and this represents a phasor. This is the phasor representation of a voltage wave which is right moving. And similarly, if you have e to the plus I kz, then you have a phasor for that voltage which represents a left moving voltage wave, right? So in phasor form, we assume that the factor of e to the I omega t is essentially constant in all parts at any given point in time. And so we just cancel out that part in some sense. And so now what we want to do is that, so we now want to rewrite our Telegraphers equation. Our Telegraphers equations and our wave equations, for the voltage and current at every point in time and space in phasor form. In other words, in the frequency domain. Now, just at the side point, so the complex voltage, of which the real part, the physical voltage is the real part of the complex voltage. So the complex voltage can be written as V of zt becomes equal to the phasor voltage Vp e to the I omega t, right? All the time dependence is captured over here, and this is just the phasor voltage Vp, right? So now if we write our our Telegraphers equations, remember this is for a lossless transmission line. So if we write our original Telegraphers equations, it was partial V of zt by partial z, which is equal to minus L partial I of zt by partial t. And the second equation was that partial I by partial z is equal to c partial v of zt by partial t. So now if you substitute the complex voltage, what you see is that the e to the I omega t factors divide out and they cancel. So in fact what you're left with is that dv of z by dt becomes equal to minus iota omega L I of zt, and the second equation for the current becomes that di of z over by dt becomes equal to minus I omega c v of zt. So these two are basically the Telegraphers equations in frequency domain, right? Yeah, in phasor form. And once again you can do what we did last time by taking partial derivatives and then substituting. So you can find that the corresponding wave equation, so these are two, so the Telegrapher equation in frequency domain for lossless transmission line, and so these are two coupled first order differential equations. We can decouple them by taking the second derivative and then substituting, and if you do that, so you find the corresponding wave equations in frequency domain. Once again, for lossless transmission lines, TL just means transmission lines, right? It's very easy to show that they basically become that d2 v by dz squared becomes equal to minus omega squared lc times the voltage, and the second wave equation becomes d2I by dz squared becomes equal to minus omega squared LC times the current I. Now so these wave equations, so they only have a z dependence. So this is our wave equations for voltage, and this is our wave equation for current. So these are wave equations. So let's solve the wave equation for voltage. Now the wave equation for voltage, let's just have a look. This is d2v by dz squared. This is equal to minus omega square LCV. So let's take a trial solution, right? I mean, you're doing differential equations in math methods. So let's take a trial solution. And the trial solution we'll take is the exponential of some mz. Okay, let's take the trial solution and substitute it. So if you substitute this, the characteristic equation becomes it's a very simple differential equation. It just becomes that m squared plus omega square LC becomes equal to 0. So m becomes equal to square root of minus omega square LC, which becomes equal to I omega square root of LC, right? Plus or minus. So the general solution, it's a second order differential equation and we have two solutions obviously. So the general solution basically becomes that V of z is equal to some V positive, which is the forward solution, e to the minus I kz, plus V negative, which is the coefficient for the left traveling solution, e to the plus I kz. And we know that, we now know what k is. And so that's our general solution. So V actually becomes V of z becomes V plus e to the minus I omega square root of LC plus V minus e to the I omega square root of LC, right? That's the most general solution, where k is equal to omega square root of LC, right? But remember that I told you that the velocity is 1 over square root of LC, so that's just the same as saying that this is equal to omega over V, right? So so this is the general solution, V plus e to the minus I omega root LC plus V minus e to the I omega square root of LC, and V plus V minus are the coefficients which give you or the amplitude of the voltage. So this is the solution in phasor form. It's implicitly implied that the e to the I omega t factor must be multiplied, and then the real part must be taken to get the physical voltage. Anyhow, so now let's consider a right traveling wave. When I mean right, I just mean that this is my transmission line, in which we have the lumped parameters, and I mean the direction of increasing z. So increasing z, right? Whatever direction that is. So if we take that case, then so for a right traveling wave, V of z is just V plus e to the minus I omega square root of LC z. Yeah, we missed the z dependence here. Apologies. So let's find the current. The current will be found, so we'll have to use the Telegraphers equations. Whenever I use the word Telegraphers equations, in my mind it's like someone sitting at an exchange in 1945 or something, and taking derivatives basically to find the corresponding current. Anyhow, so if you use the Telegraphers equation, if you use the so I mean, I'm sorry I didn't label them on the previous slide, but you can relate to this. So basically we'll just use the fact that d by dz of V of z is equal to minus iota omega L I of z. And if you use this, you basically find that minus I omega square root of LC becomes equal to minus I omega L I of z. So I of z basically just becomes the square root of C over L, that is, times V of z. So that's the current. So this is the current in phasor form. So now we have both current and voltage in phasor form. So what's the impedance? Well, the impedance in Z is just it's just V of Z over I of Z. So that's just equal to square root of L over C, right? Which is equal to Z naught, which is the characteristic impedance, and this is exactly the same impedance we derived before, right? So just to recap, we've done lossless transmission lines. So what you do is that so our way of going about it was, so our method was that first we made a lumped element model thing. The second thing we did was we applied Kirchhoff's current law and Kirchhoff's voltage law. The third thing we did was that we constructed the Telegraphers Equations, and the fourth thing we did was that we found the wave equations, found and solved the wave equations. Once we've done this exercise, we know what the voltage is, and we know what the corresponding current is, and we know what the impedance is. Why is the characteristic impedance important? Well, because it doesn't matter how long this transmission line is, as long as the inductance per unit length is L, as long as the capacitance per unit length is C. This is the impedance looking into this transmission line. So if you can match that, then you will not get any reflections, I promise you. But why and what reflections have to do with impedance, I'll show you next time. And now you know how to do this in both time and frequency domain. So I've taught you how to solve these in time domain, which is what we did last time. We just laid down our differential equations as functions of position and time. We decoupled them into our classical wave equations. We took a forward propagating solution, and then we solved. Today what we did was we looked at the phasor notation, and then we built upon the phasor equation and we did the same analysis. I will now be using the frequency domain, the phasor notation from now on to the end of the course, because it's easier and because it's more intuitive. The math becomes easy, and the physics and the engineering sticks out. If that's all good, the next thing that we want to do is we want to start And this is where things start getting fun. I'm going to start looking at a lossy transmission. I'm sorry if this is not very, if I haven't motivated this well enough. I would have tried in a live class session, but the thing is that transmission lines are they're a special form of waveguide. They have enormous practical applications, and the simple results that we're deriving here have profound consequences on the modeling of physical systems and on the modeling of engineering systems. So this is all really important from both an engineering and a physical perspective. So we want to consider a lossy transmission line, and what that basically means that we will now add series resistance as well as shunt resistance. What does that mean? So we will add a series resistance per unit length a series resistance R per unit length, and we will model a shunt resistance. So basically in our lossless model, we assume that there is no conductance, there is no parasitic flow of current from one conductor to the other, right? And so we assume that the shunt resistance is infinite. What we will do is that we will in fact model the shunt resistance. So we will model the shunt resistance as transconductance. And we will give it the symbol G, and so G will be the transconductance per unit length. And so G will allow parasitic current flow between the top conductor and the grounded conductor. So I think it's time we should draw a diagram, because we've talked a lot, and I think we need to put a picture here in order for us to understand what we're talking about. So this is essentially a transmission line. You now have some resistance. Okay, I don't like that drawing. You have to be precise when you draw your resistors. So that's a resistor, that's the inductor, this is our first branch, that's transconductance, that's the original capacitance we used to have, and this connects to our bottom conductor. Similarly, we have another resistor. So this is a series resistor, inductor, another branch, resistor, capacitor, connecting to our grounded conductor. We then have another resistor, another inductance, our transconductance, our shunt capacitor next over here, and these are our output terminals. So this resistor here is the resistance per unit length, R delta Z, inductance per unit length, L delta Z. This is transconductance per unit length. The higher the transconductance per unit length, the higher the amount of current can flow from here to here. So the higher the transconductance, the higher this, the more current can flow from here. The higher the transconductance, not the shunt resistance, the transconductance, right? Conductance is just 1 over the resistance. So G delta Z, and this capacitance is C delta Z. Similarly, this resistance is R delta Z. This inductance is L delta Z. This is G delta Z. This is C delta Z. This is R delta Z, L delta Z, G delta Z, C delta Z. Let's label our currents exactly as we did last time. Actually, let's label our nodes first. So once again, this is node 1, this is node 2, this is node 3. Once again, the voltage at node 1 is V, the voltage at node 2 is V plus delta V, the voltage at node 3 is V plus 2 delta V. And the current in this branch is I. The current in this branch is I plus delta I, and the current in coming out of the third node is I plus 2 delta I. The amount of current flowing basically flowing there is minus delta I. The amount of current flowing there is minus delta I, right? So on and so forth. So this is our new transmission line model. What we've added are these series resistances and these parallel transconductances. If the transconductance is very high, you have a lot of energy from the top conductor. It just goes to the bottom conductor and it goes out. Now, if you want to, I'll give you a physical situation where this can happen. Let's say with your headphones, you usually have you have a red wire and a black wire. The red wire usually carries signal. The black wire is the reference or ground, and they usually have a cladding or insulation around them. If you remove the insulation and the red and the black wires touch, you have a lot of current going from here to here. You basically short your transmission line. You don't hear any music in your iPhones or whatever it is you're listening to in your anyways. So point being that this is a shunt effect, and I've modeled it as a transconductance, which is the inverse of the shunt resistance. And similarly, if your conductors are rusty or whatever, you get a lot of resistance going from here to here, and so that's also parasitic. So what I just want to do is that I want to set up the equations for lossy transmission lines, and then we can solve them properly next time. So let's start with our analysis between node 1 and node 2. So the voltage at node 1 is V. The voltage at node 2 is V plus delta V. Now, between node 1 and node 2, you have an inductor and you have a resistor. So, V minus V plus delta V, right, the potential difference between these two is equal to the voltage drop across the inductor. So that's L delta Z, which is the inductance of the inductor, times partial I by partial T, right? That's the voltage drop across the inductor. Plus there's some voltage drop across the resistor. What's that? That's R delta Z, which is the resistance of the resistor, times the current, right? This is between node 1 and node 2. This is right, because if this is node 1, this is node 2, the voltage here is V, the voltage here is V plus delta V, and between these we basically have a resistor and an inductor, where this resistor has a resistance R delta Z and this inductor has inductance L delta Z, right? And so this is the corresponding equation that we've written here. Now this can be further simplified as minus delta V becomes equal to L delta Z partial I by partial T plus R delta Z times I. So in the limit that delta Z goes to 0, so the deltas become partial derivatives, so we get partial V by partial Z becomes equal to minus Ri plus L partial I by partial T. Okay, so I'll just draw a box around this and we'll call this equation A, right? Because this is the first Telegraphers equation for lossy transmission line. Now let's get our second equation. Now the current entering like going down from node 2 is minus delta I, right? We said that this is node 2. I is coming in, what's going out is I plus delta I, and the current flowing this way is minus delta I, right? And then it adds the other way, and then this is then branching out into our transconductance and into our capacitor, and then it meets here and then goes down, right? So this transconductance is, of course, this is C delta Z and this is G delta Z. So if we can simplify this, and we know that minus delta I becomes equal to, what's the current through capacitor? Well, it's capacitance C delta Z times partial V by partial T. What's the voltage at node 2? So that's partial by partial T of V plus delta V. And the other part of delta I, so delta I is divided between the capacitor and the transconductance. So this is the part which goes to the capacitance, and the part which goes to the transconductance is it's the transconductance times the voltage, right? So that's G delta Z times V plus delta V. So minus delta I becomes equal to C delta Z times partial delta V by partial T plus C delta Z times partial V by partial T plus Vg delta Z plus delta V G delta Z, right? So we have 4 terms. It turns out that we can actually simplify this to just get 2 terms. So in the terms where delta Z and delta V are multiplied, and in the term in which, so we'll ignore this term and this term. So we take this to be 0, this to be 0, and so to a first order approximation, delta I becomes equal to C delta Z partial V by partial T plus Vg delta Z. So once again, in the limit that delta Z goes to 0, we take which basically means you're taking a tiny part of your transmission line, you get that partial I by partial Z is equal to minus bracket open your transconductance G times the voltage V plus your capacitance C times partial v by partial t. And let's make a box around this. And let's call this equation B. Now, this is the second part. So now equation A and equation B together form the Telegraphers equations for lossy transmission lines. So they are more general actually than our telegrapher equations for lossless transmission lines. So the next thing we can do is that we now have the telegrapher equations which are coupled first order linear differential equations. So we can find second order decoupled wave equations. To do that, take the derivative. So take derivative of equation A with respect to z, and take derivative of equation B with respect to t, right? And then substitute. You'll find the following. What you'll find is, so the first wave equation you will find would be that del 2v by del z square is equal to LC del 2v by del t square plus LG plus RC partial v by partial t plus RGV. It's not hard to come across this. I know there are lots of terms they can this is what you get, and we will call this equation C. And the second wave equation you get is that del 2I by del z square becomes equal to LC del 2I by del t square plus LG plus RC partial I by partial t plus RGI, and we'll call this equation D. So equation C and equation D. So equations C and equation D are general transmission line equations, transmission line wave equations for a lossy transmission line. Right, so unlike the lossless case, they actually represent a physical system more accurately. Now, let's write equation C in phasor form. Now, to write equation C in phasor form, we substitute V of Zt is equal to V phasor times e to the I omega t, right? If you do that, your wave equation just simply becomes so it's del 2v by del z square becomes equal to omega square LCV plus Lg plus RC times omega v plus RGV, right? So that's the wave equation in phasor form. I can actually simplify this for you, so we can write this in a simplified form. If you basically define if you define x to be equal to iota omega L plus R, and if you define some y to be equal to iota omega C plus G, if you do that, you can basically write your wave equation for V as del 2v by del z square becomes equal to x y v. Honestly, that's all there is. And if you then further define a parameter gamma squared to be equal to x y, then your wave equation for V becomes, so if you do this, then your wave equations simply become del 2v partial v 2v by partial z squared minus gamma square v becomes equal to 0. And in complete symmetry, because the math was very symmetric, your wave equation for I becomes del 2I by del z square minus gamma squared I becomes equal to 0. And these are your wave equations for lossy transmission lines. Next time, we will solve these and look at the impedance of a lossy transmission line. We will also start looking at reflections and impedance matching. So that'll basically be, so the next couple of lectures we'll try to wrap all of this up, and that hopefully be pretty much all you need to know about electromagnetic field analysis at this stage. I hope this has been clear. Once again, we've just been talking about transmission lines. Transmission lines are two conductors which transport electrical energy. We've taken one conductor to be the ground. We've taken the second conductor as the conductor across which the voltage is applied. Well, the voltage is obviously applied between the two conductors. We've said they're uniform conductors, so they have some resistance R per unit length, some inductance L per unit length, some capacitance C per unit length, and some transconductance G per unit length. And then we've constructed, we've taken very small basically elements of length delta Z, and using those small elements of delta Z, we've basically constructed our Telegraphers equations and then our wave equations, and then we've seen the impedance at different points. I hope this is all clear about what we're talking about, and we'll solve lossy transmission lines next time. I'll be happy to take any questions in the meantime. Thank you very much.